this retreat.
No, you are not going to regret not missing. All right. So graphing is, along with kinematic equations that we have already spent a couple of days working through, graphing is going to be one of the biggest parts of kinematics. I can tell so much information from a graph. I can tell you where an object is located at a particular moment in time. I can tell you how fast that object is going. I can tell you if it's speeding up or slowing down. I can tell you what direction it's going. I can tell you a whole lot from just looking at a graph. All right, so when we start looking at graphs, I know you've studied graphs, so I wore my Graph Shapes shirt today.
Those are like the small advances.
Are they? Does she have this? Oh, does she do? Okay, well, maybe she needs to get this t-shirt.
Yeah.
All right, so when you've looked at graphing and you have graphed, you've always graphed up to this point using an equation. And yes, we are going to relate our physics to an equation, and a lot of them are going to be some of the equations that we have just learned, those kinematic equations, but we're going to be talking about real stuff now that we are applying as a graph and not always just y and x. So y equals mx plus b, and y equals x squared, and y equals the square root of x, and y equals 1 over x. Where those are actually now going to have actual physics terms like displacement or time or velocity or acceleration, and all of those kinematic variables are now going to be what we are doing this graph for. So all of the graph knowledge that you've had from math class, we're now going to translate into real objects and their motion. All right, so the first kind of graph that we're going to look at is called a position versus time graph. And so on the x-axis, we are going to graph time, and our time will be in seconds. And on the y-axis, we are going to graph position in meters. All right, so the formula for the slope, when we're calculating the slope of a graph, is what? How do we calculate the slope of a graph? When I'm just looking at, so rise over run.
y2 minus y1 over x2 minus x1.
So y2 minus y1 over x2 minus x1. Well, guess what? Instead of just y, now we're going to have position, and instead of just x, we're going to have time. So the slope of a position versus time graph is going to be change in position over change in time, because I'm going to be graphing position on my y-axis and time on my x-axis. So this is where sometimes it gets really complicated, because when you're learning the formula for slope, and you say y2 minus y1 over x2 minus x1, now in physics, we call x position, and we're actually graphing it on the y-axis. Okay? So the slope of a position versus time graph is delta x over delta t. So this is my displacement over time. Now, I have a formula on my formula sheet that says change in position over change in time is equal to some kinematic variable. Which one is that?
Average velocity.
That's going to equal my average velocity. So for right now, we're going to talk in a second about average velocity and instantaneous velocity, and that'll make more sense in a few minutes. But when I graph position versus time, the slope of my line, if it is a straight line, is going to be equal to my velocity. All right, so we're actually going to write this down. Slope of position versus time graph equals velocity. And I know I just wrote that up above, but super important that we kind of keep that straight. I write it in a different color just so if you ever go back and look at my notes, you are reminded of that. Okay, so let's graph the distance versus time of a bus's motion. Okay, so we have our position over here on the y-axis in kilometers, and we have the time in hours. So we're going to be graphing something instead of meters and seconds, we're going to be using kilometers and hours. Totally fine, because what's given to us in the problem is in kilometers and hours. All right, so suppose a bus is traveling through this city. It travels 100 kilometers in the first 2 hours. Okay, so first thing that I can assume is that because I'm not told any different, that this bus starts at position 0. All right, so when time equals 0, we're going to call that position 0. And after 2 hours, it is going to have traveled 100 kilometers. Make sense? Are we okay with that? And then it says, and 120 kilometers in the second 2 hours. So my time at that point, I'm going to add 2 more. So at 4 hours, it will have traveled 120 more. So this is going to be, my position will be about 220, so about halfway, and after 2 more hours. It stops for 1 hour. So that means that at position or at time 5 hours, it is still at the same position. And then it finishes the route by going 100 kilometers in 2 hours. So we go forward in time to time equals 7 hours, and we're going to add another 100 kilometers. So we go from 220 kilometers to 320 kilometers at hour 7. Now I am going to try, it's hard with my iPad, but I'm going to try to draw straight lines here.
Robert, if you draw one from the back, you can like hold it down and it makes it straight. And then hold it and it should make it straight. Nope, I guess not.
No, it's not. So let's look at this graph here. All right. First of all, what do we notice about the words of our problem and the direction that the bus is traveling? What do we notice, or what can we assume?
It's moving in a positive fashion.
We're going to say that the bus is moving in the positive direction the whole time. All right? So if I were to read through the word problem, it says nothing about the bus turned around and went back to where it came from, or the bus turned around and went the other direction. So when the problem does not say that it went the other direction, or it doesn't give you a negative number for a distance or a velocity or an acceleration or anything like that, then you assume that it's always moving in the positive direction. What is happening between time 4 hours and 5 hours? You know what, this doesn't actually look like what I wanted it to look like. Let's see if I can draw this better. What is happening between time 4 hours and 5 hours? It stopped. So what is the slope of the line between time 4 hours and 5 hours?
Between what?
Between time 4 hours and 5 hours. What is the slope of that line? The slope equals 0. So if you don't remember, think about slope dude. So slope dude says, when we read from left to right, we have puff, puff, positive, nice, negative, this is 0 fun. We'll never have anything that's undefined. So at that point, because my slope is 0 from time 4 hours to 5 hours, my velocity is 0. So my velocity from 0 hours to 2 hours is going to be the change in position, which is 100 kilometers divided by 2 hours, which is going to be 50 kilometers per hour. Then my velocity from 2 hours to 4 hours is going to be, what is my change in position? It's going to be 120 kilometers divided by 2 hours, which is going to be 60 kilometers per hour. And then what about my velocity between 5 and 7 hours? So that's going to be my change in position, which it travels 100 kilometers in 2 hours. So it's going to be 50 kilometers per hour. Now, if I just look at this graph, first thing I want to look at is, what kind of graph am I looking at? Well, I am looking at a position versus time graph. So this is telling me where is the bus located at a particular point in time. All right, so I could ask you, how far had the bus traveled after 3 hours? And you would look here and you would go up to this line and say, oh, well, after 3 hours, it had traveled 150 kilometers, right? So that's just reading the graph, which I know that you're familiar with, but we're going to do more practice with that. But just by looking at the graph, before I even calculated the slope of the graph, I could have told you, all right, so this bus, it traveled about 325 kilometers total in about 7 hours. And if I just looked at the steepness of the slope of the line, so this is where I will tend to, let me get one that has color to it. I will tend to use a ruler here, and I will say, okay, I'm going to put a ruler next to, this part of my graph. So is the bus moving forward or backwards? Well, this is a puff, puff, positive slope from 0 to 2 hours, so it's moving forward. Now, what happens from 2 hours to 4 hours? Well, guess what? Do you see how my slope becomes more steep? I could tell you just by looking at the graph, it's going faster now in the next 2 hours. And then what happens if I hold it up here? The slope is 0, it's flat, so it's not moving. I can also look here and say, oh, look, my position at time equals 4 hours is about 220 or 225 meters. My position after 5 hours is the same. It didn't move in that time interval. And then if I put my ruler up next to this last line segment, I can actually compare this line segment with this one and say this one is a little more steep and this one is a little bit less steep. All right, so I can actually just use a ruler and tell you a little bit about each segment of this bus's motion. All right, if I calculate the slope of each one of the points on my line, then I can calculate the velocity at any given point. So at any point here, between 0 and 2, its average velocity is 50 kilometers per hour. Any point between 2 and 4, its average velocity is 60 kilometers per hour. Between 4 and 5, its velocity is 0, and from 5 to 7, its average velocity is 50 kilometers per hour. All right? Now, if I wanted to calculate the average velocity for the entire trip, so what I'm going to do is I'll do this in a different color. Let me see here. This is going to be the slope. Why is this so thick? Come on. Let me try this one. There we go. So this is going to be the slope of the line from first point to the last point. So this is going to equal, my total distance traveled was 320 kilometers over a total time of 7 hours. And what does that give us? Oops. So total average is going to be 45.7 kilometers per hour. Right? So that's the average velocity for the entire trip. Okay? So when I have a higher slope, then that equals a higher average velocity. When I have a lower slope, that is a lower average velocity. A horizontal line means that the object is at rest or not moving. And if we had had a negative slope, it means that it is moving backwards or in the negative direction. All right, we good? We're going to skip on to page 12 and look at a couple of things real quick. And we're going to look at a couple of examples here. So at the top of page 12, you have position versus time of 3 objects. We have object 1, object 2, and object 3. So what can we say about the motion of object 1? And I'm looking at the graph on the left. What can I say there? What do you think, Shelby?
On the left.
This position. So I'm looking at this graph, and it has graphs of object 1, object 2, object 3. So Shelby, what can you say about object 1? So it's moving in the positive direction. And we can also say that this has a constant velocity in the positive direction. Vincent, what can I say about object 2?
Slope 0.
So slope is 0, so the slope is the velocity. So what does that tell us about? Its velocity is 0, and do you remember the physics term for that?
At rest.
At rest. Good. So I know what you mean when you say stationary, but I want you to try to use the term at rest only because that is going to be the most common way that a word problem will give you that information. And Joanne, what can you say about object 3?
It has a constant velocity in the negative direction.
Yes, constant velocity. In the negative direction. All right. Now, we're just going to look at the graph here on the right because this is a graph of position versus time, and it's a curve. And if we see a curve like this, this looks like a graph. If you look at my shirt here, that looks like y equals x squared. So what this is saying is if I wanted to find the average velocity, I would draw a straight line from here to here, from the beginning to the end, and I would calculate the slope of that line. That's the average for the whole trip. But if I want to find what is the instantaneous velocity at one moment in time, what I'm going to do is I'm going to hold up my ruler tangent to the line. So have you talked about tangent lines?
Yeah.
So a tangent line is, imagine like if you had a circle and you drew a line from the radius of the circle to the outside, and then an angle 90 degrees to that would be tangent line. So we have to imagine when we look at a curve that if there was like a circle inside and we drew this line tangent to that curve, at any particular point, the slope of the line that I draw would be the instantaneous velocity. So we have this example at this point right here. This is the line that is drawn tangent to that curve, and the slope of this line is 12 meters per second. Now the good news is I'm never going to ask you to actually calculate that using a tangent line. I'm never going to ask you to calculate an instantaneous velocity based on this. But what I want you to know is once we have practiced this, and we're going to practice a bunch, is I want you to be able to say that, hey, look, at this point right here, if I draw a line tangent, what would my velocity be here?
0.
It's going to be 0 because the line that is tangent to the curve at that point is 0. And then if I follow this around, what's happening is it's getting steeper and steeper. So a straight line means constant velocity. A curved line means that we have some acceleration going on. So when you see a curved line, that means that there is some acceleration. And we're going to look at what that looks like in the next day or two. So we're not going to actually estimate or guess or anything like that. Just for the sake of time, we're going to skip this example at the bottom of page 12, and we're going to go on to velocity versus time graphs, which is on the top of page 13, because I do want to look at this, and then we're going to do more with this on Monday. All right. So we've looked at a position versus time graph. The second kind of graph that you're going to see is a velocity versus time graph. And when we graph velocity versus time, we're going to graph time on the x-axis, and time will usually be in seconds. And then on the y-axis, we're going to graph velocity. And velocity will be in meters per second. So the slope of our line is going to be change in velocity over change in time, because this is the change in our y-axis, and on our y-axis we're graphing velocity, over the change on our x-axis, and what we're graphing on the x-axis is time. So the slope of our velocity graph is going to be change in v over change in t, And this is going to be in units meters per second divided by seconds. And what physics variable is the change in velocity divided by change in time? This means something in physics. So Vincent, it's on your formula sheet. Find me a formula that is equal to change in velocity over change in time.
Is equal to change acceleration.
Acceleration. So I'm going to write it again in a different color. Slope of velocity versus time graph equals acceleration. All right, so we are going to look at this graph here, and we're going to identify what's going on at points A, B, and C. So at point A, what can we say? First of all, what can we say about the part here? Let me get the colors real quick. What can we say about this segment from like here to here before it starts curving?
Constant.
It's going to be constant, and it's constant what?
Velocity.
Actually, no. If I had a constant velocity, remember
you're right,
this
you're right,
is
right.
velocity.
Acceleration.
It's going to be constant acceleration because it's a constant slope. All right? So before A, we have constant acceleration. Is that acceleration going to be positive or negative? It's positive. How do you know that, Vincent? Yes, because it has a positive slope. So think slope, dude. Puff, puff, positive. Then at point A, what can we say about?
Acceleration slows down.
So acceleration slows down some, but it is still, is it positive or negative? Because it has a positive slope. What can I say about point B?
It's on a slope of 0.
Slope is 0. So, what does that mean? If the slope of a velocity versus time graph, see, that's what we think. We think it's at rest, but it's velocity versus time. So that means that at point B, this has a constant velocity. We always, always, always have to ask, what is the graph? And this is a velocity versus time graph. So if the slope is 0 and the velocity is constant, what does that mean acceleration is equal to at point B?
0.
Acceleration will be 0. What about point C?
Negative slope.
So we have a negative slope. So
Velocity is going down.
velocity is decreasing, so it's going to be negative acceleration. It is slowing down. Now, here's a trick question. What direction is it slowing down?
Going in the same direction the whole time.
And what direction is that going to be?
Right.
Yeah, so we're going to say it's slowing down in the positive direction. So this entire trip all of my velocity is above the x-axis. So that means that the object always has positive velocity the entire time, so it's always moving in this direction. It stops at point B, or excuse me, the acceleration stops. So it's speeding up, speeding up, speeding up, speeding up, not quite as much, and then constant velocity, and then slowing down, not slowing down quite as much, slowing down, then slowing down more. And what happens at this point here?
Stops.
It stops. Its velocity equals 0 at that point. All right? So velocity equals 0 when it touches the x-axis. So do you see how much information I can tell you about the motion of a car or a train or whatever it happens to be just by looking at a graph?
Is that all?
That is not all. All right, they're gonna call us here in just a minute to go to this college fair. So let's talk about this graph down here. First of all, what kind of graph is this?
Velocity time.
Velocity versus time, okay? So let's talk about from 0 to 10 minutes. And of course, most of our velocities are going to be in meters per second, but this one, of course, is not in meters per second, because why could we get an example that has standard units when we can use weird ones? Okay, so let's talk about from 0 to 10 minutes. All right? What can we say about the velocity? Is it positive or negative?
Positive.
So a positive velocity. Joanne, what does it mean that it's positive velocity?
That it's speeding up.
So positive velocity just tells you something about direction, not whether it's speeding up yet.
Teachers, please excuse this interruption. At this time, please dismiss 11th grade to head over to the gym for the Christian College Fair. Teachers, you are also needed to go if you are able to help monitor students. Again, please release 11th grade students at this time so they can go to the Christian College Fair. And any senior that received an email from Mrs. Shiver and has not gone to the fair is welcome to go. 11th grade to the Christian College Fair.
Okay, let's finish this and then I'll let you go. Okay, so the fact that our velocity is positive just means it is moving in the positive direction. Now, what else can I say about its acceleration from this point? From 0 to 10 minutes, what is its acceleration? It's constant. Is the acceleration positive or negative?
Positive.
Why?
Because the number is increasing.
The number is increasing, and
The
what?
velocity is increasing.
So what can I say about the slope of my line?
It's positive.
Positive. Positive slope. So, what is the acceleration from 0 to 10?
Calculate the slope.
We can calculate the slope.
No. Is what
It's
we're
not
doing?
that hard. Yeah, we are.
Okay.
It's not that hard.
A pencil. Because mine ran out of lead. That's why.
Shelby, how would we calculate the slope from 0 to 10 minutes?
Y2 minus y1 over x.
So what is y2? So I'm looking from here to here. 60 minus 0 meters per minute divided by 10 minus 0 minutes is going to give me an acceleration of 6 meters per minute squared. All right, so let's look at from 10 to 15 minutes. What can I say about its velocity between 10 and 15 minutes? Constant. And Shelby, what can I say about the acceleration between 10 and 15?
It's a negative acceleration.
So I'm just looking at from 10 to 15 minutes.
Oh, sorry, it's constant.
So it's constant, but what is the slope here? Between 10 and 15, it's 0. So slope equals 0. So acceleration equals 0. All right, that's where we're going to stop for today. We were going to pick up with the negative slope on Monday. And I'm going to let you guys go to the college fair. And by the time I walk over there, my next class will be here. So,
That was a lot easier than you made it sound.
okay, well, that was a lot less than I had planned to do.
Oh, okay. Because
So-
I was like, no joke, I came in here today terrified. I was like, what are we going to learn today?
Wait until you get Monday. So my intent was to give you a website and then make you match some graphs. So we'll do that on Monday. All right, see you guys.